Good evening, everyone. So, welcome to the online discussion on course Water and Wastewater Treatment that is being taken by Professor Manu Prasad Pelanki from IIT Roorkee. My name is Manyatnam Prakash and I am from IIT Kanpur. I am a PhD student here. So, as a part of my PMRF duty, welcome to week 11 of this discussion. This is second last online discussion. There are one more say online discussion left that will happen on next Tuesday. So this is our general schedule that we meet on every Tuesday at 7 from 7 p.m. to 9 p.m. via Google Meet. And the recording of this session is being uploaded on this YouTube channel, which has been already been shared with you. So if you want to go back and check previous session and want to clear some doubts, you can always go back. So there are total 3 TH in this course, so you can access the material that is being discussed by all 3 TA. Is available on different YouTube channels that has been already been shared with you. So in week 11, these 5 topics were discussed. That is adsorption isotherms, ion exchange, nanofiltration and RO, aeration and removal of iron and manganese from wastewater from water. Okay. So it's been expected that you have already gone through the video lectures. So as you know that I cannot discuss all 5 topics here. So the question has been taken from previous year. So I will be discussing some of the concept related to adsorption and adsorption isotherms, and the question related to these 4 topics. Okay. So the number of question which have generally our task is that some question has been shared with us and we have to discuss that is being expected in your Qs and future exam and all these things. So the number of question for this week was very low. So what I have done that first I will be discussing details regarding adsorption, concept related to adsorption and adsorption isotherms in details, and after that there are some around 7 question, 7 8 question that I will be discussing it one by one. So if you have any kind of doubt, you can raise your hand or you can write in chat box. Okay. So I will be going through the concept of this adsorption. Okay. So in a word, if we actually there are 2 terms. In one generalized term we use, that is sorption, that anything that is solved on, suppose there is some contaminant, say uranium is there or chromium is there, arsenic is there, and you want to remove that contaminant from your water. The best way is to miss. There are many techniques that either you can use some chemicals that will precipitate out those contaminants, but those are very costly, and those kind of process generally produce some kind of sludge. So scientists or researchers have developed some mechanism that is called sorption. So they use some kind of material. So what will happen that those material, when are added in the water containing those contaminants, those those materials will what will happen that those materials will get attached to the material which we have added. So in a common term, this process is known as sorption. That we are the contaminant which was there is getting sorbed on what material which I have added in my water. Okay. So this sorption is again divided in 2 portions, that is adsorption and absorption, AD and AB. So that is absorption and adsorption. These two things are very different things. But in this course, I will be only focusing on adsorption. Remember, not absorption. Similar term is also, it's related to surface thing and volume thing. You can always go to some standard book. Yeah, you can check what is the difference between this AD and AB. Okay. So as an environmental engineer, one should have an idea of about this. What is this sorption is a common term. Either the process can be AD, that is adsorption, or the process can be absorption, depending upon which type of process, means how that contaminant is being removed from the water. Okay. So what now remember? So now what will happen? What happened that this was the surface which I have provided in my water, and now there is a contaminant, say arsenic. I will be focusing on arsenic. There are many contaminants, but general contaminant which I am studying is arsenic and chromium and all these things. So now what will happen that obviously this arsenic remains in the form of some kind of oxidized form. So it will arsenic is in either form of ASO4 to ASO4 3 minus something, SO4 3 minus something like that. Just you can check in which form of arsenic is always present in the water. So that is negatively charged, and your surface should be positively charged, so that there should be a bonding between those two materials, so that this the arsenic which is outside or in your contaminant can get attached to your surface, and that's in that way your water will be free from contaminants. So there is some kind of intermolecular force which is acting between your surface and your contaminant which is present in your water, so before going deep into what is this adsorption and what is this absorption, so I will be discussing about this intermolecular forces. So this concept you must have been might be aware of this. What are different kind of intermolecular force, that is electrostatic force, then van der Waal force, then hydrogen bonding. So this type of force, so and there are some kind of chemical forces also, but that is different thing. So in a way, this intermolecular force is defined that these charged particles. So what I was saying, that I have to remove one contaminant, so I have to this is already my contaminant is already charged, so I have to provide some surface which is also charged, so that there would be a kind of some intermolecular force, so that will help to remove my contaminant from my water. Just 1 minute. Mm, sorry. Mm. So these intermolecular force, from name itself suggests that it is between molecules, inter and molecular force, the forces between molecules. The charged particles and ions in the aqueous system are attracted or repulsed to form to from each other. Either it will be attracted to each other or repel from each other, mainly through the electrostatic force. Okay, the one predominant force which acts, yeah, which helps in the removal of those contaminants is this electrostatic force. Okay, so the charged particle are necessarily polar and hydrophilic. Okay, so what will happen, that these terms are very common to you, I think. I hope you are aware of these things. So, but basic thing means I am just building up some of the basics so that you can understand what is this adsorption and absorption. Okay, okay. So however, it is said that relatively weaker attractive or repulsive forces also exist between uncharged particles and molecules. These forces are together termed as van der Waal force. So you must be aware between of this term, that is van der Waal force. So when two charged particles are there, they have some kind of diffused layer. So if those particles are very apart from each other, the forces acting on them will be not so, either it will be repulsive, or suppose one is positively charged, another is negatively charged, so it will be attractive force. But when when both of them are positively charged, it will be a repulsive force. But still, if we want to bring it together, so the concept of this van der Waal force is introduced. I'm trying to explain it in much easier way. I hope you are understanding this. So in uncharged in uncharged polar particles and molecules, remember this, what is polar and unpolar, which have polarity are considered as polar molecule, and which don't have any kind of polarity. I hope, yes, I am assuming that you know these things. If you are not aware of those things, just you can just take a few minutes and you can search on what is this polar and non-polar molecules. Okay, so all I am trying to do is just in uncharged polar particles and the molecules, such as van der Waals force originate from the intermolecular attraction between dipoles and hydrogen bonding. So again, what happened that when two particles started to come between the started to come between started to form together some kind of bonding. So either it will be the common term is used van der Waals forces, and the mechanism behind these van der Waals forces include this hydrogen bonding and all these things. Okay. So, however, intermolecular forces also exist between non-polar particles or between the polar and non-polar. So, generally, see, all these things are dependent upon your charge. What do you call charge? Surface charge. Okay. So either it will be like either those particles will be getting attract to each other, or it won't be getting attract to each other. Okay. So here what is happen that this intermolecular force see, if we look in the broad sense, that if two charged particles are positively charged, it will always repel each other, or if two negatively charged particle is there, it will always repel each other, and if one is positive, one is negative, it will always attract. But that is on bigger sense. But if we look at the intermolecular sense, you have to apply many concepts like of this wonderful force and this hydrogen bonding and all these things. Okay. So this is what is being written here. How means intermolecular force also exists between non-polar particles. So imagine there are no two non-polar particles. There are no two non-polar molecules. Okay. So it is being said that the intermolecular force can also act between these two non-polar particles also, or between polar and non-polar, which we already know that between a non-polar and polar there will be some intermolecular force by basic definition. But sometimes people tend to think that there won't be any kind of intermolecular forces between those two same type of particles, but it doesn't happen. But theory or research has many paper have been published, or research has been done where it has been seen that two non-polar particles can also exist by this non-polar forces, non sorry, intermolecular forces. Okay. So in what happened that again the just 1 minute, again 1 minute. Hmm. So in polar molecule, electrons are equally shared. However, within a bond, electrons are constantly moving. These results in creation of instantaneous dipole moment in non-polar molecule. This give rise to van der Waals forces effective over very short ranges. Remember, these van der Waals forces only acts when the distance between two particles are very short. The polar molecules may have also induced dipole moment in polar molecules, leading to the attractive van der Waals forces such as interaction are also effective. See, uh, we all know that this polar and non-polar will attract each other. But what happened that this the concept of van der Waals forces are always introduced when the sort when the distance between these two molecules or particles are very short. So, in summary, if two neutral particles can brought very close to each other, they will experience a mutual attraction due to van der Waals force. So, remember this concept means the main theme of this discussion to write out all these things, polar and non-polar molecules. That you should not have this idea that two neutral particles won't attract each other. They will attract each other. That also that depends upon the distance between those two particles. You must have seen this kind of graph, that is between this force and distance. Okay. So generally what will happen that initially this is attractive force, sorry, this is repulsive force, and this is attractive force. So generally what happen that when this kind of graph is plotted. So when the distance between two particles is very low, the attractive force dominates, and when the distance between the particle is very high, this repulsive force dominant between those two particles. Hmm. So the depending upon this the type of forces, or depending upon the characteristic, that we know that the two neutral particle might attract each other and all this thing. So what happened that we define something, this adsorption. Remember this adsorption and desorption, partitioning of molecule between solids and liquid phases. So remember what I was saying, initially, this adsorption. This was initially I was saying about this initially I was saying about this uh, sorption thing. Okay, sorption. So sorption can be divided into two portions, that is AD, and there is one another term, that is AB. Okay, so what happened that now imagine there is one contaminant, say arsenic. This arsenic is, and there is one thing which is known as solvent. Okay, so now what happened that, and these are all in a beaker. So now what will happen that this arsenic will get attached to the on the surface of this thing only, will get attached on the surface of this solvent. Okay, consider this as a S. Okay, so this arsenic will get attached on the surface of this. Then this phenomena is known as adsorption. Why adsorption? Because it is happening on the surface, only on the surface of this contaminant. Now in another system, now consider you have something, some molecules and some kind of contaminant in your water. Now to remove that this contaminant, what is happening that it is incorporating itself uh, in the volume of these particles. Okay, so then this phenomena will be known as absorption. Okay, so in a simple term it is defined as if the sorption is happening on the surface of the solid, it is known as adsorption. And if the phenomena is happening in the volume of the solid, means inside this volume, then it is known as absorption. Okay, a, B, and A, D. Okay. Now, what is this option? Once what happened that once this all the arsenic from these particles, when all the arsenic from this particle has been in this water has been removed. So I will take out this bigger material, and what will happen that I will because my main target is to reuse this solid now, because we are getting more contaminated water. So my main target is to reuse this solid. So what will happen that I will desolve, yeah, remove these attached arsenic particles, any kind of contaminant. So I will be adding some kind of acid or something to remove this thing. So the concept is known as desorption. Okay, so what happened that this happened between solid and liquid phases only. So I will be just giving one some insight that how this happened. Okay, how this adsorption and desorption happen. So this is what I am saying, that remember this was your contaminant, C was your contaminant, and this was your solid. So remember this solid is negatively charged particles. So depending upon the pH of the system, this thing will be either positively charged or either it will be negatively charged. So currently the pH of the system is in such a way. Hmm. currently the pH of the system is in a such a way that this particle is positively charged, sorry, negatively charged. So uh, to increase the efficiency of the particles, so we know now, imagine a case that to if someone ask, just remember, just forget what I mean. So initially this is your particle which is negatively charged, and negatively charged, it is because of the pH. Okay, pH is in a such a way that it is negatively charged. So there is one contaminant, and what will happen that this contaminant will get sorbed, okay, or you can say adsorb also. So remember, if you are not knowing the mechanism, either it, whether it is adsorption or absorption, you can just simply use the term of sorption. But if you are sure that here adsorption is happening, but that all the removal is only due to the removal is only by this attachment on the surface. So you can use the term of this absorption. Okay, so what is happening that this is negatively charged and this is C. So so what will happen that it will just simply form a bond between this is it will have some kind of charge also. It will be either positively charged or negatively charged. So depending upon this negative charge, it should be preferably positively charged, so that it can easily form any kind of bond. So right now we are not showing any kind of bond, but so what will happen that this will get attached to this will form a some kind of bond, and it will be removed in that way. So this sorption can be either this physical sorption or chemical sorption, that is physical sorption or chemi sorption. So this is mainly due to electrostatic force. So remember, here we are forming some kind of bond, that is this S minus and C. So here they are forming some kind of bond. So that's why it is known as chemisorption. So remember, there will be a huh. So remember, what will happen that there might be a chances, there can be a case where what is happening that they are not forming some kind of force. So they are not forming some kind of bond. So S minus was there. So with some kind of electrostatic force, it will be just attached on the surface of this thing. Okay, so then that will be termed as physical sorption, or that is also known as physical sorption. So these two kind of sorption is generally absorbed, seen in this nature. So this obviously this physical sorption will be a big kind of sorption, and this chemical sorption will be a strong kind of sorption. So if you are removing something with the help of chemisorption, the bond will be strong, and the removal efficiency will be high. But for this physical sorption, the bond will be not so strong, and it won't be giving you good result. Okay, so again this partitioning thing is happening. So here, due to this hydrophobic interaction. Okay, so I hope you remember this hydrophobic interaction. Hydrophobic means this fear of water. So what is happening that in this case, what will happen that this particle, see, whatever the contaminant is there, so it is remember, this was your water, and it contains some kind of water. Okay, so as this molecule is hydrophobic, means it don't want to be, it don't want itself, it don't want to be in water. So because it has hydrophobic nature, so what will happen that this particle will find some other surface other than water. So what will happen that this will attach itself on the surface of this thing, and that's why this is known as partitioning, or that is adsorption due to hydrophobic interaction. Here also adsorption is happening, but it is happening because it has a hydrophobic nature, means it do not want to live in water. So it has some other surface. Okay, so different kind of examples are there. Miss, different kind of example has been already shared in your online discussion also, miss, about GAC, that is granular activated carbon. So apart from in your, if you have attended your online session all the discussion are is based on this GAC only, that is granular activated carbon, something like that only. So apart from that, other example has been also been shared, but here just look what kind of example I am sharing. Okay, the interaction between a hydrophilic surface, hydrophilic, remember hydrophilic, which has a fear, means hydrophilic means the surface means that do not want to form any kind of bond with water, and the hydrophilic molecules. Okay, hydrophilic surface and hydrophilic metal. Sand, silt, clay particles are present in water or sediment in contact with water and charged are hydrophilic. Okay, remember hydrophilic means attracted toward water. The hydrophilic portion of the on the amphibic organic molecule in water may physically solved or chemically solved on the sand, silt, clay, and thus form a hydrophobic coating on the previously hydrophilic surface. Okay, so I hope this is clear statement. Example of partitioning is this thing. An uncharged hydrophobic molecule C. See, remember this is uncharged hydrophobic. This is phobic. May approach very close to hydrophobic particle surface and hence can attach to it due to van der Waals forces. So remember this is also hydrophobic substance also, means molecule only. It also do not want to form any kind of bond with water. This one also don't want to form any kind of bond with water. So with time, what will happen that these two will come together and it will form some kind of bond with each other, and finally it will, that contaminant will be removed from the water. So this is kind of simple partitioning thing. Okay, and this was the example of this adsorption. Okay, so this note that a hydrophilic molecule in water experience forces due to dipole moments and hydrogen bonding in aqueous phase and hence cannot approach close to particle easily. Remember, this hydrophilic is already forming some kind of bond with water present in the system. Water has H plus and OH minus, so as that is hydrophilic, so it is already forming some kind of bond with water molecule present in the system. Okay, and that's why it is experiencing some kind of forces. So that's why these particles cannot approach any another particle which is present in the system, and I want to remove that particle. So what is happening that these hydrophilic molecules may not have miss, they are trying miss chemistry may suggest that this can remove, but it has already forming some kind of bond with water. So this might not be giving a proper efficiency for removal of water, removal of that contaminant from water. Okay, similarly note that similarly note that a polar or charged particle has a diffuse layer which cannot be easily penetrated by hydrophobic molecule C for close approach. So remember, as if you are paying attention to my lecture, is what I am saying. I have discussed about this particle have some kind of diffuse layer, alpha layer, beta layer, and diffuse layer. This kind of layer generally means you can just go and check different layer around a molecule. So in water, if you search this thing, you will see that there is one alpha layer, beta layer, then there is one diffuse layer. Okay, so due to this diffuse layer, there is also some kind of problem in formation of some kind of bond, a physical bond, a chemical bond. Okay, so mass transfer of molecule from water to solid and vice versa by transferring. So remember why this mass transfer, because I want to remove whatever is present in my water, I want to remove with the help of some kind of sorbent. Okay, so remember you will so this is general kind of reaction, that whatever C kind of molecule C. So when I have added something in the water, it will have some kind of concentration. It will have some kind of concentration, say X gram per liter. Okay, and it will have also some whatever molecule, whatever the contaminant, what present in the water will have some kind of concentration, say X molar, X millimolar. Okay, so what will happen that with time it will get adsorbed on the surface. So as this has a fixed concentration, Q has already a fixed concentration. Actually I am representing what is this Q. I will be defining later. So obviously this Q is concentration of in a solid phase. So this Q has fixed concentration. But what, and remember, whatever solid is there. So if you have gone through the lecture, you must have aware that it has some kind of surface area, and it has some kind of maximum absorption capacity. So what will happen that this C will be getting absorbed on the surface of this solid, and that this sorption can happen up to certain limit only. It cannot absorb on all the solid, all the contaminant from the water. So what will happen that after some time, it this whatever initially x concentration was there, after some time the concentration will be by, and say this concentration is equilibrium concentration, so that will be referred as CEQ. Okay, CEQ, that is concentration of C at equilibrium. So whatever the constant, remember, whenever a reaction happen, suppose A is going to B, so we know that a equilibrium constant is defined. So for partitioning equation, the term whenever remember why I am using partitioning coefficient, because initially there was some initial concentration of C, it has get solved on the Q, so some partitioning has happened. So that's why what will happen that and see the concentration of molecule in water. So after some time, what will happen that it will C will achieve some equilibrium. So the equilibrium constant which is given by Q divided by C equilibrium. Okay, where Q is the concentration of solid in uh, concentration in solid phase, Q is concentration in solid phase, C is concentration of molecule in water, and Kp is liter per kg. Y unit you can match is the partition coefficient. Okay, so I hope this is clear to you. Okay, so remember what is happening, that now my task is to see that how this means how this concentration vary with either time or either concentration of this Q. Okay, or uh, just we want to see the variation of those things. Okay, so we plot something called isotherm. Okay, so isotherm is equilibrium relationship between the liquid phase and the solid phase concentration of contaminant. Okay, so what will happen that obviously this initially this is in liquid phase. Okay, so after some time what will happen that it will get solved on this Q, the solid which I have added. So now this C has partitioned itself in the two form, that is one in liquid form, that is form that is that then that will be termed as liquid phase concentration in equilibrium, and also some of the C has get attached on the solid phase, so that is known as solid phase concentration of this contaminant. So isotherm is defined as equilibrium relationship between the concentration of these two. Okay, so either it will be linear isotherm. So what will happen that this Q, whatever the concentration is in the solid phase, is directly proportional with some constant to the equilibrium constant of this C solved in the system. Okay, so so what remember this was the CS, that is concentration in solid phase, concentration of molecule in solid phase. Okay, and this is Q is the concentration of this Q is the concentration in the solid phase. Okay, is the concentration in the solid phase. Okay, so what will happen that assumption before plotting something we assume something. So the surface area available for partitioning is much larger than the concentration of solid in the solid phase. Okay, so what will happen that this Q is all. So remember there are generally three type of isotherm has been defined. The first one is this linear isotherms. Similarly, two other kind of isotherm has been also defined. Okay, two other type of isotherm has also been defined that will I will be discussing in next portion. So as it is a linear isotherm, so what is happening that as the concentration is concentration this so what is happening there, this concentration in solid phase is linearly increasing with the value of Cs, okay, and this coefficient is known as this Kp, that is partition coefficient, okay. So this Kp depend upon the molecule being solved and the nature of the solid phase. So these are parameter of this Kp, okay. So this is like simple linear isotherm, okay. So determination of this partition coefficient of hydrophobic organic molecules to soil organic matter. So somehow this method can whatever you have learned from here, you can just interpolate in other for other molecule also, for any kind of inorganic molecule also. Okay, the partitioning of such molecule is due to hydrophobic interaction with natural organic matter solved on soil. Okay, for most hydrophobic organic molecules, the octane water partition coefficient is known. Remember, this is a well-known thing. If you, I don't know, I have not gone through the online lecture, but this octane water coefficient is well-known thing for hydrophobic. Whatever we have to define our hydrophobic system in some kind of coefficient. So best or universal method is to define in this octane water partition. So remember what happened that here also in water, how this octane is also kind of some kind of organic pollutant, organic matter. So how this there is partition between water and octane. We defined its coefficient, and that is known as KOW. Means water is going from octane to this from octane to means there is partition between octane and water. Okay, the partition coefficient to the soil organic matter KOC and KOW is related by a relationship of this type. So we know this is a standard relationship which you can find in any standard book. Okay, to find this, generally what happened that we plot the, remember this is a generalized form, this is general equation, so I'm not introducing something new. So this if it is getting new to you, I will suggest there is some standard book that is just let me share one that standard book. You can just always refer to, you can always Hmm. There is one this book by Water Chemistry by Mark Benjamin. So you can go, and I think it is chapter whatever I am saying. I am studying for hmm. Whatever I am saying, I am presenting from this book, that is Chemistry of Metal in Aqueous Species, the solution phase reaction. Okay, so here you can see. Uh, huh. Here you will be. Uh, I don't know. I think this is older version of book. Okay. So, sorry. I am just whatever I am doing here. I am doing from this book. Okay. So, and this chapter, that is adsorption. Okay. Page number. Hmm. Adsorption reaction. Okay. So whatever I am saying, I am just saying from this book only. Okay. How this you can see adsorption, desorption, adsorbate, absorbent, sorbate, sorbent. So if you have any kind of doubt, if you are not getting what I am saying, just you can go and check this book. And here you can see miss, they have also written some kind of reaction and all these things to make you understand in a better way. Okay. Hmm. So this KP can be hmm. So this Kp, that is fraction, is known as FOC, and FOC is fraction of organic carbon on soil, and that generally varies between zero point zero zero 0.001 to zero point 0.1. And from here, and KOC, all we all know that. So during solving any kind of example, this KOC will be given to you. So this KP, actually, see, I might be doing something wrong here, because I am discussing something which I assume that you are aware of those things. Okay, so I'm sorry if you are not getting these things, but if you just pay a little bit attention, you will be like, if right now, if you might not be feeling familiar with these terms, but if you are planning to do masters, you have higher study, so you at some point you will study this thing, because these I have taken these material from that book, and some of my older class. What do I call it? This? My class notes that the miss during my btech, I was not also aware of these these things, but with time I just came to know what are these things. Okay, so there is one simple example. Whatever I have said, you have to put values here. Okay, and you can find it. Just we will look into this example. So a 2 liter of water is half filled with water and half filled with air containing 200 milligram of sand. 1 millimole of toluene is added in the system and expected to absorb all organic matter present in the present. So Henry constant, that is Kh for toluene, is given. Log Kw of toluene is 2.73. Organic partition coefficient, that is KOC. See, every data which we required for this equation is already given. Okay, okay, and remember a value is also given. So you have to, what is the equilibrium mass distribution. So what will happen that uh, this was water, it contains some kind of sand. Okay, so toluene has been added in it. So what will happen that some of the toluene will get absorbed on the water, some toluene will remain in toluene form, and some of the toluene will get absorbed in this mm, on this sand. So you have to find at equilibrium what will be the concentration of these three things. Okay, so I hope everyone is aware of this formula, gas constant formula, that is PV is equal to nRT. Okay, so I will be using this concept to solve this equation. Okay, so at the equilibrium let the equilibrium concentration in water, whatever initially I have added, how much I have added, mm, 1 millimole. So remember, 1 millimole means 10 to the power minus 3 mole. Okay, let the equilibrium concentration in water C. NW in water, so NW will be equal to C. So you using Henry constant, remember this how if you miss, if you have gone through this second last lecture, I have discussed about this Henry constant, because whenever miss suppose there is one water system, and what some air wants to get diffused in this water or want to get dissolved, then it depends upon the Henry constant, means that is directly proportional to this partial pressure and all these things. I hope you are aware. So using Henry equation give one formula that whatever concentration in water will be given by C into P, K into P, where P is the partial pressure of toluene. Okay, so and pressure, how can I find this pressure? Pressure will be given by P equal to PV equal to nRT. So P will be C by 0.15, that is C concentration, a molecule, mole in water, and Kh, that is already given 0.15, and this Ng RT divided by Vg. Okay, so Ng the moles of water in gas phase, Vg the volume in of gas phase. Okay, so Ng will be C Vg divided by 0.15 RT. C Vg, we have already know the volume of the gas is, how much volume of the gas is given here. Okay, 2 liter of glass jar. Okay, uh, see, 2 liter half filled with water, so 1 liter is for water and 1 liter is for air. Okay, So see, 0. Mole already given to you. R value is 82.05 into 10 power minus 6 to 93 degrees Celsius. So that will be 0.277 C. So log KOW already given to you 2.75. Therefore log KOC will be 0. So here from here we can find the value of log KOC. Okay, and we know that so from here that this KOC will be coming. I will be taking this log, and we already know this thing formula. We have already know that this KP will be given by FOC into KOC. Okay, so this KOC will be 331.15, that is itna gram per liter, and Kp will be KOC into FOC. So 33.0 the value of this was 0.001. Okay, and this Q, we know that this is a linear isotherm, so Q will be given by Kd into C. Okay, Kd again diffusion partition coefficient. Okay, so moles of the, so in the solid phase, uh, this Q is a moles in the solid phase, so that will be given by mkpc. So I have this Kd I have converted into this uh, in the terms of mole. Okay, so again it will be 0.2 into 33.11 into C. Okay, where is the m is the mass of absorbent. So so now we know that I have added total, I have added how much? I have added 10 to the power minus 3 millimole of toluene. Okay, and we know that either it will be in the form of, in the gas form, or it will be in the solid phase. Okay, so this C, and either it will be in the water form. So C in the water plus C in the gas plus C in the solid, it will be total equal to 10 to the power minus 3. So so C will be given by C will be given by, that is 1.226 into 10 to the power minus 4 mole. Okay, so I can, at equilibrium I can find this NV will be NV we have already defined in the term of C. NG will be 0.277 into NW, and this NS will be, sorry, this NS will be 6.62 into NW, that is this much mole. So out of 100%, 12% will be in the water, 3% will be in air, and 83% will be get sorbed all the soil. Okay. Hmm. So this is very simple question. You have to just mass balance, and you have to know this formula. Okay. KOC minus KOW. From there you can just uh, find out this concentration in each and every phase. So now till now I was defining linear isotherm. Okay. So now I will be discussing about this non-linear isotherm. So non-linear isotherm. So what happened that in till now what we were seeing that hmm, hmm. Till now what I was seeing that there is a linear relationship between this Q and CS. So generally, what happened that this generally occur with organic molecule, like organic molecule. But in real system, we also deal with inorganic things. Okay, like arsenic, chromium, fluoride, uranium, manganese, lead. So these when the remover when we want to solve these material or something, generally linear isotherm is not absorbed, so it is non-linear thing. Okay. Hmm. So I will be discussing what are those non-linear things. So in many cases, the isotherm is nonlinear due to finite adsorption capacity. So what happened that in those linear isotherm, what happened that uh, this this sorption was not so good. Only some on surface on something, a small efficiency was not generally seen good. Okay. So, but what happened that due to this finite sorption capacity, so now you have somehow you have modify your samples, you modify your solvent. So what will happen that its surface area or the porosity has increased. So what will happen that its adsorption capacity of the solid has increased. Okay, so let St be the total site. So but we know that on this mineral there will be some kind of site, some site will be there here and there. So on that site, this molecule will come and get attached. Okay, this molecule will come and get attached. Hmm. So remember this St is the total number of site and Ac is the total number of free site and total number of molecule occupied site. So St will be given S plus Sc, and there will be always some kind of equilibrium between this S and Sc. Okay. So similarly, so what will happen that if we want to write the equilibrium constant for this will be Sc given by S plus C equilibrium, and we know that this S is given by St minus Sc. Okay, and so here I can substitute it, and let M be the mass of adsorbent. Then K, I can again substitute this thing here, and after substituting this thing, I will be and we know that we also know that this has a some kind of maximum absorption capacity. So again, I will come at one equation, that is Q is equal to Q max into C equilibrium K 1 plus C equilibrium into K. Okay, and this is known as Langmuir isotherm. Okay, so this is the isotherm which is generally common, practically seen in removal. So whenever if you are reading some kind of research paper on adsorption, and they are saying that this material is being removed by this thing. So here what happened that this the isotherm which is seen means how the pattern is seen, that is versus Q versus QS. It will be this type. It will be like this. Means it will be the material concentration will be getting adsorbed, but it will happen up to certain limit only, and that limit is Q max. Okay, and this Q max is defined as the maximum adsorption capacity of that material. Okay, C equilibrium is the concentration of material in dissolved form at equilibrium. So please remember, so this will hmm, hmm. So what will happen that whatever contaminant is present after whatever and this material is there. So once this has maximum absorption capacity has reached, or no further absorption can happen, so this will attain one certain equilibrium concentration, and that will be known as CEQ. Okay, CEQ. So that is written there. The Q is equal to Q max. You can, so this is also derivation of this Langmuir isotherm term also. There is one more isotherm, that is fan release isotherm. That is empirically based formula where there is no derivation, but you can derive this Langmuir isotherm. Okay. So this Langmuir isotherm is given by Q is equal to Q max K, C equilibrium into K 1 plus C equilibrium into K. Okay. If C equilibrium K is much less than K, we can write Q is equal to Q max plus C, and again this is a linear isotherm. Okay. So you can say that this Langmuir isotherm is a advanced or modified version of linear isotherm. So if we modify, and what kind of modification, if we assume that C equilibrium into K is much less than 1, obviously then this can be neglected. Then that linear isotherm can be considered as a what do we call linear isotherm can be considered as a isotherm, linear isotherm. Okay. Hmm. Can be reduced to linear isotherm. This is what I said. This is the graph which I have already said. Linearizing, you can just linearize it, and you can then plot. And remember Another term which is empirically based on some experiment, it is given that Q is equal to Kf into C equilibrium into 1 by n. Empirical thing used when adsorption capacity is finite but not at all objects. Means remember, but we have assuming that all the surface have are identical. Means all sides which is getting absorbed here are identical. Means surface area at all the of the all sides are equal. But if that is not the case, we have to use some other definition, other formula, that is known as Freundlich isotherm, that is Q is equal to Kf into C equilibrium the power 1 by n. Okay, so linearizing, again this will give you this formula for any, again here for n is equal to 1, you can see this thing, the this isotherms can be reduced to linear isotherm. Okay. Hmm. So again, one example is there which I will just discuss in short, because for solving this thing you have to know in detail what is this isotherm. So miss, I have tried to give you only just formula, but before solving this you have to know the basic concept also. But I think you can solve this question because I have given you sufficient information how this adsorption thing works. Okay. Hmm. An experiment is conducted to determine the sorption isotherm for benzene on activated carbon. To conduct the experiment, three 1 liter jar were filled with water plus 1 gram of the activated granular carbon (GAC). Remember, this was being discussed in your lecture. Different amount of benzene were added to each jar. Then the equilibrium concentration of benzene that remains the water is measured. The experiment data are projected in the table below. That when 2 gram of the benzene was added, the equilibrium concentration in water was 1. When it was 10, it was 3.29, and when it is 50, it is 10. Okay. So now remember, they are asking to solve using the Freundlich isotherm. So QE is equal to Kf into C to the power 1 by n. Okay. So where C is the equilibrium concentration of benzene in water, and Q is the equilibrium mass solved per unit mass of solvent. Okay. So Q is defined in that way. Hmm. So solution, coming to the solution, we know that QE. See, remember this formula was not discussed with you, but Q when I define this thing, this is known as capacity, also known as also known as this thing that is also known as density also. So how we define it is, how we define it, concentration in solvent divide sorry um, how we define Q as uh, um, concentration or amount of chemical solved divided by concentration or amount of solvent, okay, present in water. So what in our case, what is being solved, benzene is being solved on what, on carbon. So how we have defined Q, we have defined the amount of or chemical amount or concentration of a chemical that is being solved, that is milligram of benzene, and the amount or concentration of solvent, here solvent is carbon. So that's why we have written Q is equal to benzene, mg benzene divided by gram of carbon. Okay. Hmm. And C, we all know that the concentration, equilibrium concentration in water. So a milligram benzene divided by liter. Okay. So total mass of benzene added will be Ce into, so the sum of them benzene will be in the water form, will be in the water, and some of the benzene will be in the solid form, that is getting solved. So total mass will be Ce into V, volume of the water, plus QE into mass of the carbon. Okay, remember you can just match the unit mg per gram, so you have to multiply it with my mass, and here it is you have to multiply it by the volume. Okay, so where VW is the volume of the water, that is 1 liter, and the mass of the carbon, that is 1 gram. Okay, so in each case this two was constant. Okay, so we knew that Q is equal to MT minus CE. Remember what is this QE? QE is the mg of solid. Mg of solid means in that is getting solved. Okay. Hmm. So what is getting solved? Um, so what is getting solved? This much amount of it getting solved. Okay, so this is what we have written. This mt minus Ce divided by Vw divided by mass of carbon. So friendly isotherm Q is given by Kf into C, and linearizing log Q is this thing. So what we have done for all three cases, we know that this MT, that is 2 gram, 10 gram, 50 gram. We also know CE, 1 gram, 3.1 gram. So we can find this QE by putting this, and we know the all the value. Then we can plot, we can get this value QE, and also we can get the value of this log CE and log QE. Okay, based on this formula. Okay, so from examination, from analyzing it, we can say that this log kf is equal to 0 or log kf is equal to 1. Okay, and from jar 2 data, 1 by an we can calculate, that is 1 by 6, and from jar 3 also we can calculate, that is 1 by n is equal to 1.6. So and how we have defined, we know that this log q is this much. We are putting this QE value, and we are putting this kf value we already know. We are calculating this 1 by n. We already know what is log ce. Okay, so if these two value were different, I would have taken the average of these two things. So by default it is coming 1 by 6 for both the cases, that's why average is 1.6. Okay. Hmm. So our task was to determine this kf and 1 by n. Okay, so we have already find this kf. Again, remember this kf, again we have taken average. Okay, so I can this kf, it come out to be 1. Okay, and this a1 by n come out to be 1.6. I hope this example is very clear to you. So now remember, we have also discussed about the kinetics. So what is this kinetics things? That this kinetics things, that we know that with time our concentration will be either obviously decreasing. So initially concentration was C, with time the concentration is decreasing, and we know that the order of reaction, it can be either uh, it can be either first or zero order reaction, first order reaction, second order reaction. So again for adsorption also, when we perform the experiment of adsorption, so obviously for adsorption we collect sample at several interval. So for this also we collect sample at several intervals at T1, T2, T3, T4, and concentration will be C1, C2, C3, C4, and the so we will exam based on, first we will define which isotherm is there, and again we will see that either it is a first order reaction, or it is a second order reaction, or it is a zero order reaction. Depending upon that, we can, there is something called advection diffusion method. So that is not part of this, but this the concept of advection diffusion was discussed in the first lecture. Some basic things, what is this ADR equation. So in ADR equation, there was one term, uh, we generally call modified ADR equation. So what happened that we know our normal ADR equation. So in that ADR equation, we know that this just represent how the concentration of any pollutant is either increasing or decreasing. So in that equation, what other term is added? If suppose we assume that the particle which is being removed, it is either getting absorbed or solved. Okay. So in that equation, one another term is also defined. Okay. This thing we already know that linear isotherm is given by this thing, linear isotherm is given by this thing, and linear isotherm is given by this thing. Okay. The adsorption kinetic, how fast the equilibrium is reached. The solid phase, there are four sequential steps: transport from the bulk to solid vicinity of the solid, transport across the aqueous boundary layer adjacent solid, that is field diffusion, then transport in the pores of the solid, that is pore diffusion, then actual absorption of the contaminant. The absorption portion is actually desorption portion is actually in both adsorption and desorption process. Step B and C are controlled by diffusion and hence are the rate lifting. Therefore, country. So remember, this is theory things. But I have not discussed about this first order, second order, zero order reaction. You have already know this thing. So just I will just just for your recap. Just let me check. I don't know in which lecture. Yes, Nikita. So, so uh, if you have any kind of doubt, you can ask. Hmm. So here you can see that generally this kind of kinetics is also seen in what do I call adsorption also. This zero order reaction, first order reaction, second order reaction. Okay, but here I was saying that the thing which I have written here is like mm, exact mechanism how this adsorption happens. So what will happen that this is your solid, this is your bigger particle where it's solvent, and this is your contaminant C. So what will happen? Transport of bulk fluid to the vicinity of the solid. Okay, so what will happen that this will be first reaching here. Okay, then transport across the aqueous phases or adjacent layer. So we know that this is our molecule. Okay, so it will have some. So just I will show you how this diffuse layer is there. Okay. So just in this picture you can see uh, here. Just here you can see that it has some kind of diffuse layer. So generally this is your surface. So initially say it is positively charged, then again there will be a diffuse layer where so it will be creating some kind of potential. So you might have a study about zeta potential and all these things. So that all depend upon this diffuse layer and all these thing. Okay. So this is distance between potential and thing. So what will happen that hmm, so this was your solid, this was your solvent, this was your contaminant. So first contaminant will come here. So again obviously it will have also some kind of diffuse layer. It will have also some kind of diffuse layer. So what will happen that there will be a interaction between those two diffusion. Transport of pores into the, now what will happen that whatever the diffusion layer of this will be, this one it has some whatever, there will be a transport between those three, and finally it will either chemically adsorb or physically adsorb on the surface of that solid. Okay, so this was a main concept. Means now this process can be either first order, second order, or sorry, uh, the decrease in the concentration of C can be either first order, second order, or third order. I have already said. Okay, so remember this is what I is given. So this is a boundary layer. This is a bulk of water. So what will happen that solid is yes. Mm. Uh, this is what I am is this is numerically written here. You can see that this is representing as a first order reduction. So initially C concentration was C. After some time concentration will be C. So dq by dt means decrease in the concentration will be directly proportional to the first order, that is C. Generally for our dc by dt, what we write, dc by dt is equal to dc by dt dc by dt, sorry for the handwriting, dc by dt is equal to kc. Okay, so we just assume that either concentration, that's why there is one negative sign. Okay, but in adsorption we know that there will be some initial C concentration, and that concentration will obviously decrease. So that's why we have fixed our CI, and at any time the concentration will be C. So the change in concentration or rate change in concentration will be directly given by dq by dt into km into C initial. Okay, so this is what happened, and whatever the fourth thing which I have written here, this fourth thing is being represented in the this just forget this pie chart, but you can see that this pore particles has come and attach itself in the layer. Okay, so this was all the discussion which I wanted to do, but as you know that I have to discuss some of the previous year questions. So generally there are total 7 questions, and this question is being taken. I hope you might have solved this thing. So in this question, if you have any kind of doubt, you can always ask. So I will be going one by one, and I will be just I will be trying to explain each and every option. And if you have any kind of doubt, you can just raise your hand. Okay. The activation of carbonized material involved. Remember what is this activation? So you have taken some material, say carbon. So what will happen that it will have some. Now this, if you have gone through the lecture, remember this adsorption depend upon site, number of site, then what is the surface area and all this thing. So now remember you have taken one solid, and you just realize that it do not have some kind of not it doesn't have number of sufficient site to get to absorb any material, or it is not providing sufficient surface area, so you want to activate it. Okay, so how will you activate it? So you will, there are several process. The process either involve exposure to the steam, pyrolysis, or formation of pores and fissures. Yeah, there are several techniques, but for this question they are asking that are these four option good, or means which of the options are correct for activating this. Activating means we are trying to increase the surface area and all this thing. Okay, so the first option is exposure to the steam. So when we expose to the steam activation also known as physical activation. Remember. So a steam activation, also known as physical activation, involves the heating material in the presence of steam at high temperature. This we all know. During this process, the high temperature cause the carbon atom to rearrange and create a network of pores within the material. So if we are uh, remember, initially there was no pores. Your surface were flat. So all the carbon were uniformly arranged, so there was no portion. No, upon heating, some mechanism happened that some pore has been defined. So now a pore has been defined, pore has been developed. So it will be giving some opportunity for some other contaminant to get absorbed in the on that particle. So a one option is correct. Okay. This steam reacts with the carbon, leading to the removal of volatile component formation of additional pores. Pores increase the surface area of the material, which is crucial for adsorption process. So option A is correct. Coming to option B, pyrolysis. Pyrolysis is the process of heating organic matter in the absence of oxygen. In absence of oxygen, okay. In context of carbonization, the involves subjecting organic materials such as wood, coconut shells, and coconut shells or coconut to high temperature in absence of this leads to breakdown of organic molecules in the carbon residue. Pyrolysis is the first step of creating carbonized. Again, here is whatever you do, either you heat it in absence of oxygen or either you heat it in presence of oxygen. This will always lead to increase in the surface area, okay, or increase the number of surface pore size. So as the pore size is increasing, the number of site is increasing. So the number of site is increasing. So what's happening that what's happening? So the absorption capacity is increasing. Okay, the formation of pores and fissure. Obviously, these two activities itself is increasing the pore and fissures. Okay, so during the both carbonization and activation process, the material undergo physical and chemical transformation, the result in the creation of the pores and fissures. These pores and fissures provide a large surface area for adsorption and allow a molecule to diffuse in the interior of the material, enhancing its adsorption capacity. So all these options are correct. So the answer will be all of above. Okay. Just 1 minute. Actually, I have some. Hmm. So all of the above are correct. So again, in summary, we can say activation of carbonized material typically involves exposing to certain condition to increase the surface area porosity. Remember, we want to increase surface area porosity and making it more effective for various applications. Okay, the process can involve exposure to steam, which I have already discussed. Uh, these steps are commonly employed to enhance the absorption capacity and the other formation, making it widely used in various industries such as water treatment, air purification, and chemical processing. Okay, so this GSE use of GSE is very common. People are using to remove many things. Okay, you can just search on. Always remember, if you want to see something scientific, always search on Google Scholar. Type Google Scholar And if you want to check that what is the use of GSE, just type GSE removal process and go to some this you will see cited by. So on research paper where there is more citation, always try to go and read that paper, so you will be getting more idea. Okay, just don't read any random thing which is present in the uh, hmm. Huh. So just don't read any random paper. Okay, just this. I think this is what I needed to share. Like if you are if you are miss scientific miss kind of researcher, or you just want to check any relevant thing, just always search on Google Scholar related to any kind of education. Okay, just don't go to just if you search anything randomly on Google, you will get many things. Okay. Hmm. The question is second question is physical sorption and chemical sorption. You have to match the following. There are non-specific binding, specific exchange of electron, typical non-reversible, reversible, common type of absorption. So really used in water treatment. Okay. Hmm. So the first is the physical absorption. It will be matching with non-specific binding, reversible, and common type of absorption mechanism. Physical absorption involves non-specific binding of the molecules to the surface of the adsorption material. It is irreversible. Sorry, it is reversible. Remember what I said, that it will be just simply attaching to the system. S was there and C will come here. Okay, and it will attach itself. Okay, it will attach itself. So by simple mechanism, this bond can be easily broken. So that's why it is known as reversible, meaning that adsorbed molecule can dissolve, return to the solution under appropriate condition. This mechanism is common in various adsorption process. Okay, so it is non, or remember this is also miss, there is no miss a specific thing that it will attach. It can attach anywhere. Common type of adsorption mechanism. Yeah, this is general common type of adsorption mechanism. Second comes the chemical sorption. The characteristics are a specific exchange of electrons. So remember, if you just I will just again show you the first picture. So here see, there is change of electron. This was S is losing one electron and C is coming here. So there is some kind of change in electron. Okay. Hmm. So there is some kind of change in electron. Okay, and rarely it is non-reversible. Yeah, once for the form is bond is formed, generally it won't be reversed. Rarely used in water treatment. Yeah, which actually physical adsorption is not physical. Uh, generally, actually, this option was actually. Hmm. Generally, it is used. Rarely used. Actually, it is commonly used. I don't know why they. I think it should be matching with physical absorption. Okay. So chemical absorption involves the formation of chemical bonds with the absorbent molecule on the surface of the. It typically involves a specific exchange of electrons, leading to the formation of covalent or ionic bond between the absorbent and the absorbent. Remember, this is contaminant, and this is the surface which is providing for adsorption. Unlike physical adsorption, chemical adsorption is typically non-reversible. While physical adsorption is commonly used in water treatment due to its reversibility, chemical absorption is less complex due to irreversible nature and potential for more specific interaction. So reason for saying is rarely used, it is defined here by because it is non-reversible and we cannot use that material again. But it is not generally seen. You can use miss generally for a miss we have developed one arsenic filter. for removal of arsenic. So generally there what happens, some kind of chemical absorption is happening on iron surface. Chemical is this on iron, this arsenic is coming and getting attached. So similarly for removal of fluoride we are using something called dolomite. So there also some kind of chemical absorption is happening. So dolomite is calcium magnesium carbonate material, and on that fluoride come and get attached. Okay, so if you want to read this thing, how this arsenic is getting attached, how arsenic is removed, just go and search arsenic filter using biocide filter, arsenic filter using removal using iron surface. Okay, just you can search and you can, we will be getting many research paper. Okay, the question again, third number question is related to um, third question is related to activated granular activated carbon. GAC is heterogeneous media for adsorption. Only neutral or non-synthetic organic can be removed by GAC. The more hydrophilic compound is, the greater its tendency to get absorbed to GAC. The polar compounds are typically not removed by adsorption by GAC. Okay, so this means I won't be going on the detail because this was very much discussed by course instructor during discussion. So I will just uh, suggest you to go and read those lectures. Okay, so but again I am just discussing in short. Okay, so granular active the statement was granular GAC is heterogeneous media for desorption. So this statement is correct. This statement is correct. The GAC is indeed a heterogeneous media for adsorption, meaning it possesses a diverse range of pore size. Again, this pore size means the same thing, porosity and all these things. Okay, a property allowing you to absorb a wide variety of molecules. Okay, only natural or and not synthetic organic can be. This statement is incorrect. GAC can be removed both natural and synthetic organic compound. It is widely used in wastewater to remove organic contaminant regardless of their uh, sources. So remember, many GSC, I think, hope you must have gone through the lecture and you might have seen that what where these GSC are used. Okay, so and also remember, I don't know, activated charcoal. There is something called related to GSC, something called activated charcoal. Okay, so what this activated charcoal has been used in many places, like many places say, I don't remember whether it has been used to removal of fluoride or not, but you can just search where can we just let me search activated charcoal, activated activated charcoal. So activated charcoal has been used to remove for removal of copper, zinc, and it is very you miss activated charcoal is used in very common way, miss commonly miss you have many person uses face washes, and that face washes say that it contains some kind of activated charcoal because those things contain some, it has very good adsorption capacity. So whatever dust particles are there on our surface, it can get easily absorbed via those activated charcoal, and we feel fresh and all these things. So yes, so activated charcoal is very commonly used. So and so saying this thing that only natural and not synthetic organics minerals. I'm not remembering which synthetic organics, but many study has been saying that this synthetic organics can be used, synthetic organics can be removed from it if it is causing some kind of contaminant using this GSC. Okay, the third option is third statement was the more hydrophilic a compound is, higher its tendency to get absorbed to GSC. The statement is generally incorrect. Remember, I am saying generally. It is correct in some context also, but in general it is incorrect. The tendency of a compound to be absorbed by GSC depend upon its specific properties and interaction with the carbon surface. While hydrophilic compound may have same tendency to absorb GSC due to polar interaction, it is not universally true, and the absorption behavior may vary widely depending upon the compound. See, I am not giving any kind of examples because if I go, miss so I will suggest you to miss. I can just give you idea that this statement is correct and this is incorrect. But if you want to go and look into examples, you can always go and search on this Google Scholar thing. Okay, Google Scholar or ResearchGate. So you can just type this statement and you can get some example. Yeah, means how why they are saying that. But depending upon miss after you see when I was preparing this slide, I was just doing this kind of research only. So I am just trying to get the gist of the statement. So miss I am just generalizing the thing. So it is saying the tendency of remember this GSC means obviously for removal of any particles depend upon their the specific interaction. Okay, so this statement is also incorrect. Okay, so the last option is the polar compound. Again, you are familiar with the polar compound are typically not removed by adsorption by GSC. The statement is incorrect. Sorry, the statement is correct, not incorrect. There is a typo mistake. Is generally correct. Remember. Hmm. Polar compound can indeed be removed by adsorption or GSC. In fact, polar compound are often exist strong interaction with the surface activated. Remember, activated presence. This activated charcoal has some functional group OH, and it this polar compound is we know that it contains some kind of charge, mis electron, unpaired electron, and all these things. So there is some kind of proper interaction. So this statement is correct. So that can form a hydrogen bond or other polar interaction, that is van der Waals force and all these things. So the statement is correct. So the answer of this question will be this. I hope you are getting what I'm saying. I'm just avoiding any kind of examples. For example, I'm asking you to refer some standard books which I have shown you in the start of the lectures, or you can just search on the Google Scholar. Okay, but here I'm just saying that what are the possible outcomes, yeah, possibility uh, about this statement and all this thing. Okay, again one numerical question is there. Absorption capacity of the following again it is based on friendly isothon. This is Q total, that is 73.4 into C total. Into C total is equilibrium thing. Okay, C is in milligram and Q is in milligram per sample containing 0.65 milligram will be treated in a batch C to reduce the concentration. Now see here C is 0.022, C total is 0.222, the required activated carbon. So you have to find the solid concentration. Okay, so remember, if you know what I have what was the definition of Q, so what is the definition of this activated things. Okay, so this Q2 is given by 73.4. Okay, into we know that C is 0.0, so this Q total is 74.60. Okay, and we know that this C total will be this C. Remember, this C total will be given by C total of toluene plus C total. So what will happen that whatever this toluene I have added, it will be remaining in the it will some will be in the water form and some will be attached to this solid which I have added. Okay, this. Sorry. So it will contain some kind of solid. So the toluene which I have added will be some will be in the water form and some will be in the solid form and some will be in its original form. Remember the example which I have discussed in the first uh, I have discussed this kind of example. Okay, so the C total you already know that you have added C total of 0.65. So out of this 0.22 is in original form. So and 76 point is the total Q which has been adsorbed. Okay, and you have to find how much is the required activated charcoal, and that will be given by CAA. Okay, so from here you can find this CAA will be 35.80 milligram per liter. Okay, so this was a simple example. So you have to just substitute the value, and you should miss if you should use the concept of this example, that we know that when toluene is added, it will be in the form of toluene, solid, aqueous and gaseous phase. Okay, but in our case there was no gaseous phase, only aqueous and solid phase was there. Okay, so that's why here you can see that only Q total, and this toluene in the form of toluene, that is aqueous phase, and in the form of solid phase is given. So based on these three, so I have discussed two example of friendlies. There was no example of there was another isotherm, language isotherm. So I'll be just discussing one example of um, this example I am sharing from my class notes. Okay, just wait a minute. The question is based on language isotherm. Okay, na? No, this is not. So remember, this is a question from my class notes that was asked during my masters. When I was doing masters, so there was some course, water and solid interfacial process, solid and water interfacial process. That complete subject is related to adsorption only. Okay, so I will be discussing only one thing. Okay, now. So here just remember, so just what happening that just focus on these three, he- from here to here. Okay, so they are saying that a solution initially contains this much of cadmium, 100 um, micromolar. Remember, micro, not milli, micro, that is mu molar dissolved cadmium, and no solid was there. And again, and after that x gram per liter of iron oxide was added in the system, and some adsorption has happened, and you have to find the final concentration. Okay, so how much solid, so here say suppose 4 gram of solid was added. So for what you have to find out that how much of this how much will be the final concentration, and you know the formula of this, you know the formula of Langmuir isotherm. Langmuir isotherm is given by this equation, that is where that is Q is equal to Q max CE divided by K into CE. Hmm. So this Qmax, so in your this Q is the maximum absorption capacity which is already given in the system. So Qmax is given to you 100 plus X. So generally the question which we in our examination, the question is asking, means every student is given some kind of a random number. For my it was 4. So that so generally it is to avoid to, so it is done to avoid any kind of cheating, so that two person sitting beside have to do their own calculation. So what happened that so initial concentration was 100, solid concentration was this 4 gram per liter. Qmax is 118, that is 114 plus x, and Kl is also 1.05 mu m per, that is micromolar. Okay, so we know that this Qmax Langman isotherm is given by Q. Here I this q is equal to q max, which we all know. Okay, so here what will happen that, and we also, I have also defined one thing, that what is this q is amount of chemical sorbed and divided by solvent concentration. Okay, so that will be c naught minus c divided by solids. Okay, so what will happen that I will be first substituting my values here, that is q is equal to q max. Hmm. I will be substituting my value Qmax, that is this one, 118 into K, that is 1.05 into CE. I have to find CE, divided by 1 plus KE is 1.05 into CE, and again here C naught, it is 100 minus CE divided by 4, and I will, these two are same, so I will be equating, and I will be getting one quadratic equation with coefficient A is equal to 1.05, B is equal to 396.6, 391.6, and C is equal to minus. You can solve this quadratic equation, and you will be getting this. Sorry, you will be getting this. You know this under root B square minus 4AC divided by 2A. Okay. Hmm. So I will be putting this value, and after that C I will be getting the concentration. Means when I added 4 gram of solid in the water, I was getting from 100, from 100 microliter to, I was getting a final concentration of 0.25 microliter of concentration. So this around 99.99% of cadmium was removed from the surface by adding just 4 gram of solid. Okay, so I hope this is miss when you have seen one example of this friendlies. This was a example of Langmuir isotherm. Okay, I hope this is clear to you. Hmm. So again, this was all related to adsorption. Now another thing related, there was some more concept related to this thing. Mm, hmm. Related to this mm, RO and all this reverse osmosis, ultrafiltration. So there is one question: reverse osmosis membrane falling occurs due to chemical scaling. Okay, chemical scaling means deposition of some kind of chemicals. Okay, so reverse osmosis, this statement is true. So this is, there is no hi-fi science behind these questions. If you have gone through the lectures, you know the basic concepts. But I will just try to let you know the some of the basic concepts. Okay. So reverse osmosis membrane falling can be indeed occur due to chemical scaling. Scaling happens when the certain ions or minerals are fed in the water fed reaches concentration where they participate on the surface of the RO membranes. This lead to formation of scale layers, reducing the effectiveness of the membrane and ultimately the causing falling. Therefore, the chemical scaling is one of the main cause of the RO membrane falling. Okay, so what will happen that there is this thing. I hope you have seen the reverse osmosis. Uh, sorry. So remember, what is this actually happened? This confused between this. So what is this membrane following this means we use some kind of membrane. So what happens that generally particles are getting absorbed here, or attached here. So if this Hmm. So, so it is kind of creating. So we know that water will be here. A certain kind of pressure will be applied. So water will a treated water will be getting here. So now happen with time. What happened that due to presence of some chemicals adsorption, this membrane get blocked. So this process is called membrane folding. So this happen due to presence of some chemicals. You are reverse. That's why it is say that when we have to perform RO, make sure that your water is very clean, means already pre-treated. You cannot just do RO on normal water, means untreated water. You have to do pre-treatment, because this is first membranes are very costly. So means I mean, if you are just raw, you are passing raw water, then you might be facing this kind of problem, that is membrane falling and all these things. Okay, therefore chemical scaling is, so this statement is true. Okay, in general soil possesses certain cation exchange capacity due to presence of negatively charged clay particles. Yes, this is also true. The soil typically possesses certain cation exchange due to presence of negatively clay particles. The clay particles have a surface with negatively charged that holds only positively charged, and this cation exchange capacity is essential for soil fertility. So I hope this is clear to you. Means this, if this is your soil, we know that it contains silica, and it is SiO2 SiO42 minus, I don't know, SiO42 minus, it is SiO42 minus, I don't know, just you can check SiO44 minus, I don't know, but you can always check. So this is negatively charged, and this is available on all the site. Okay, just to check, confirm it to what I will be just referring to one of my. Hmm. So remember, it is SiO2 polymer. Okay, so you can see that um, the in common it is negatively permanent charge which is there. Hmm. So you can see that it contains this SiO2 polymer, and due to this a different kind of a sheet like a structure is there, and depending on the pH it depends on the many things, but in common what is happened due to presence of this silica material, it is referred as negatively charged, but depending on the pH of the system it can be either positively charged. At low pH, what happens that H plus due to presence of high H plus, this H plus will get attached here, so it will make the surface positively. At neutral pH, it will be neutral, but at higher pH, which is generally in case of our soil, that is we know that so it is negatively charged. But in common, if you search on the in any paper, you will see that our soil is negatively charged. Okay, so this is the kind of a structure which we see. Okay, so hmm, so this statement is also true. Okay, the final question is this thing, that consider the following statement. The correct sequence for the attraction of typical ion exchange region for calcium magnesium strontium will be first calcium, then first strontium, then calcium, then magnesium. The affinity of ion exchange material is higher for the metal with a smaller hydrated radius. You have to find this. You have to correct statement. Hmm. So the first statement that the correct sequence for the exchange is first will be first strontium will be adsorbed, then calcium will be adsorbed, then magnesium will be adsorbed. Okay. Oh, sorry, it will be exchanged. Okay. The statement is correct. In general, the exchange tends to great affinity for the higher charge than the lower with the higher charge and lower hydrated radius. Okay, the strontium has highest charge and typically largest hydrated radius among these ions, followed by calcium and magnesium. Therefore, the sequence is likely to depend on the order of attraction to the typical ion exchange regime. I hope this is clear to you. And the second statement is that affinity the smaller hydrogen. The statement is also correct. The in ion exchange process, the affinity of the ion exchange material is generally higher for the ions with a smaller hydrated radius, which I have already said. The smaller ions can be more easily fit into the exchange site on the region, leading to the stronger attraction and higher affinity. Okay, both the statement A and B are correct, and statement B the correct explanation of the A. Therefore, the C is the correct answer. Oh, sorry, I don't know. C will be the C the correct answer with the both are correct and B the correct explanation of A. Okay. So if anyone have any kind of doubt, you can ask now. I have tried to explain each and everything. So you can just either you can type or you can just raise your hand. We have 5 minutes. I will be here till 9 p.m. So yeah, Nikita.
Good evening, sir.
Evening.
Sir, can you tell me how to prepare for the exam?
You are in which year?
What, sir?
You are in which department? Civil,
Civil.
and you are from which college?
Graphic era.
And which semester? Means second year or third year?
Sir, third year.
Okay, so you are asking for GATE or any other examination?
Sir, examination, water resource treatment.
No, no. Oh, this examination. Now you. Sorry, sorry.
Uh,
I understand. I misunderstood you. I think you were asking about some competitive examination. For this examination, you can expect the question which was being asked during this thing, Miss. Doing assessment, you were given some kind of question, na? So
yes, sir.
similar type of question you can expect in your examination, and there are high chances that some of the question will be already been have been solved by you. So you can expect a similar type of question. The question will be mainly focused on this thing, multiple correct thing. Okay, na miss choices will be given to you and all this thing. So I will suggest you to go through the all the questions that has been discussed by I think you have joined for in my case you have joined for the first time. If you are you have been attending other TH, so go through the question which he has shared, and if you have not attended it, no problem. You can just go through the question which have been given to you in the form of assignments. So you can expect similar questions.
Okay, sir.
and
Thank you.
and if you want to miss some other question has been also discussed by some th, so I think you have been given a link of one Google Drive where all the PPTs are there and solved questions are there, so you can always go and check those PPTs.
Okay, sir.
Okay. Any more doubt? So if you don't if anyone miss, there are only two-person. So Durga, if you have any kind of question, you can ask, or we can just in the meeting here. sir. Okay, so I am just ending the meeting here. Okay, good night. Tata.
Okay, sir. Thank you.